Hello, this is Group A. My name is Ariana Garita,
I'm McKenna Hill.
and this is determining the charge of a balloon.
So the purpose of our experiment is to calculate the amount of charge and number of electrons transferred between two repelling balloons after providing them with a negative charge.
Our information. Electricity is made up of a collection of electrons. If electrons are in motion, we call them current electricity. If electrons are not moving, this is static electricity. The stroking motion removes the number of electrons from clothes and then deposits them onto the balloon, creating then static charge. Electrons have a negative charge, and in class we learned that objects with like charges tend to repel each other, and objects with opposite charges tend to attract each other, which is why the balloons stick to the fabric and the person holding them.
So the models we used for this experiment were the equations of F net equals F tension plus F electric for the x direction, and F net equals F tension plus F gravity for the y direction. Our system schema included our balloon stand, Earth, and the two charges. Earth and the two charges have gravity between them, and the charges have electric potential between them. The charges in the stand have contact force and tension force between them. And on the right is our force diagram for this experiment.
Well, setup. The interactions from this experiment included Coulomb's interaction, electric force, and that's the equation right there being displayed, tension force, and gravity force. The two balloons were suspended from two strings of equal length from a meter stick, which was propped between two chairs. The balloons against our clothes, and then we let go of them to observe the interactions between the two like charges.
The assumptions that we made for this experiment were that the balloons were the same size, mass, and charge, the balloons were completely neutral from the start, that air resistance was negligible, that each balloon repelled at the same distance from the original position, and that F net was the sum of all forces, and by Newton's first law, F net was equal to 0 at equilibrium. That we collected for this experiment was that the mass of each balloon was 2.88 grams, the length of the strings that we used were 50 centimeters each, and that F net equals the sum of F tension, F electric, and F gravity. The resulting forces on the balloons would cause each string to hang at an angle of 12 degrees from the vertical.
Coulomb's law of force between two charged balloons is displayed on the screen. We rearranged the equation in order to find our value of charged. In order to find charge, we needed to look at the x and y components to accurately solve for electric force. We use force of tension and force of gravity in order to solve for electric force. And then we use tangent in order to relate the two angles. Bottom left corner of the screen, you can see our developed equation in order to find Q. The distance R was calculated by multiplying 2 times the length sine of theta. Here we show our unit conversion that we needed to use in order to solve for Q. The final value of the charge was found to be 0.170 times 10 to the negative 6 coulomb.
The final charge of our balloon in coulombs and divided that by the charge of 1 electron to get the amount of electrons transferred between the two balloons, which would be 1.06 times 10 to the negative 26 electrons were transferred when we charged the balloons.
From our readings, we understand that rubber is not a good conductor of electrons, so these are bound to stay in the surface of the balloon once we transfer them by rubbing them in our clothing. We can trust the value calculated for the amount of electrons transferred to each balloon, since the balloons were not rubbed greatly, therefore they were not expected to be charged greatly. Thus, they did not repel each other that far apart.
Sources of error were that we would not have been able to know if the balloons were neutralized between adding charges. Therefore, our calculations may include previous charges that weren't accounted for. The balloons would be attracted to the person holding them before releasing them to interact with each other. And the balloons never fully stop moving when recording data, so the angle and calculations may not be exact.
In order for us to have trust the data more or to have more accurate data, we should have attempted to have multiple trials. We experienced difficulties when recording the data since the balloons were suspended at a distance that was very close to the ground, so they would interfere with our clothing, with people walking around, which will produce air resistance or wind. So in order to avoid this, mind suspending the balloons in a place where there could be no interference from nearby objects or subjects, like in a high altitude, while still suspending them with a ruler. And an interesting thought we have after completing the experiment was, what if we could get different amounts of electrons transferred in the balloons by rubbing them at different surfaces? So perhaps when repeating this experiment, consider using a very thick sweater, a light piece of fabric, and etc.
Thanks for watching!